Okay, here we will come to a very important topic of this chapter, and this topic is about Faraday's experiment. So, Michael Faraday, he took a coil and a galvanometer, and this galvanometer is a very sensitive galvanometer, and he connect this galvanometer in series with the coil, as shown in this figure. Okay, so now he also used a magnet, a bar magnet, which consists of a north pole and south pole. All right. Okay. So what he did is he take this magnet, and when this magnet is stationary, he found that the galvanometer, right, shows zero deflection. It means that the galvanometer is at rest. Okay, or it doesn't show any deflection. Okay, but to his surprise, when he moved this magnet, right, with its north pole towards the coil, and he's moving the magnet in this way, he found that this galvanometer deflect. And when he moved the north pole of the magnet towards the coil, then the direction is right, because okay, this galvanometer, it is actually an instrument which is used to detect the presence of current. When the galvanometer shows deflection, it means there is a current in the circuit. So as the galvanometer deflects by moving the magnet, it means a current is flowing in the coil. And this current, when the north pole is moving towards the magnet, then this current is flowing in this direction. Okay, so this is the directions of motions of current. Okay, now as he move, and then again he stop. Okay, when he stopped, again he found that this galvanometer again comes at zero, which means the galvanometer did not deflect in this case. Alright, now he's trying to move, right? He tried to move this magnet again away from the coil. That means he's moving this north pole away from the coil. Again, he found that as he moved the magnet this side away from the coil, he found the galvanometer once again deflect. But the deflection in this case, it is opposite to the previous one. Here, the galvanometer deflects towards right, but when he moved the north pole of the magnet away from the coil, he found the galvanometer is deflecting in the opposite direction. Okay, so similarly, he's trying in many ways. That is, he tried to move the south pole of the magnet also towards the coil. As he moved the south pole towards the coil, then what happened? The galvanometer also shows deflection in this case, and the current it is passing in the coil in this direction. Okay, so therefore, after this experiment, Faraday made these following conclusion. The first conclusion is that a galvanometer deflects when there is a relative motion between the coil and the magnet. Okay. Second conclusion is this directions of deflections in the galvanometer is reversed when you reverse the motion between the current between the magnet and the coil. Third, the deflection is increased if the magnet is moving faster towards the coil or away from the coil. So these are the conclusion which is being made by Faraday in his experiment. Okay, so now after this experiment, this Michael Faraday, he explained about this current which is produced in the coil, and that is because if I say this is a magnet, but this is the north pole. Okay, we know these are the magnetic field lines. So these magnetic field lines are actually right large in number. So when he move this north pole of the magnet towards the coil, then what happens? The magnetic field lines which are entering the coils, okay, these number of lines starts increasing. So as the number of lines increase, then what's happened? As they are increasing, right, then there is a deflection in the galvanometer. But when he stopped the motions of the magnet, let's say at this point, right, suppose he stopped the motion. When he stopped the motion, then what happens to the magnetic field lines? The magnetic field lines will become constant. Okay, so for the magnetic field lines which are passing through the surface, we call them as magnetic flux. Okay, so when the magnet is moving, it means the magnetic flux are changing. So when the magnetic flux increase, right, we get a current in the coil. And when he moved the magnet that side, it means the magnetic flux starts decreasing. So when the magnetic flux are decreasing, then again he found a deflection, which means there is a current in the coil. So moving a magnet towards the coil or away from the coil always produce a current in the coil. And this current which is produced in the coil, it is different from the current which you obtain from the cell. Okay, suppose this is a cell, right? So this is the current which is produced by the cell. And this current here, it comes from the chemical energy of the cell. So the chemical energy of the cell, right, it converts into electrical energy. But in this case, the current which is present in the coil by moving the magnet, this current here is known as induced current. So this induced current, it is actually not produced by the chemical energy. Not like in this case. In this case, we have a source of current is due to chemical energy. But in this case, the source of current is actually due to the motions of the magnet. So when you move the magnet either towards the coil or away from the coil, it means you are doing a mechanical work. So I can say that this induced current here, it is produced from the mechanical work. Or I can say, in other words, this mechanical energy, it is converted into induced current, just like a chemical energy in this case is converted into electric current. Okay, so these are the explanation about Michael Faraday's experiment. Okay, now going ahead with this experiment, okay, Michael Faraday made two laws, and these two laws, right, they are very important. Okay, let us see about these two laws of Michael Faraday. And these laws here are known as electromagnetic, okay, induction. Okay, sorry, I think it's Michael Faraday's law. Okay, it's Michael Faraday's laws. So there are two laws of Michael Faraday's. Okay, first law. What does the first law say? The first law says that the the magnetic flux, or whenever a magnetic flux that is linked with the coil is changing, then an induced current is, or a current is induced in the coil. So please note down that law. First law says what? Whenever a magnetic flux linking with the coil is changing, then a current is always induced in the coil. So that is the first law. So I will write here just to remember. Changing magnetic flux produce current in the coil. What current? Induced current. Second law. The second law says that the magnitude of this induced EMF, okay, magnitude of induced EMF, magnitude of induced EMF, it is directly proportional to, or it is equals to, the rate of change of magnetic flux linked with the coil. Okay, or I can say for this magnetic flux, sorry, this is the magnetic induced, okay, I made a mistake. This is the magnitude of the induced EMF. Yes, suppose I'll denote this induced EMF by E, then this Michael Faraday says that this EMF which is induced in the coil, it is equals to the rate of change of magnetic flux. Okay, so this is the mathematical statement of second law of Michael Faraday. Alright, so now you may ask me a question, what is this induced EMF? Alright, okay, again let me remind you, when you have a cell, okay, then this cell produces a current, and the potential difference between the two terminals of the cell is known as EMF. Okay, so we get a current because of this EMF. Okay, but in this case, do we connect any cell in the circuit? No. But there is a current. In this case. So when there is a current, it means there is a fictitious, I can say fictitious battery, which behave like this cell of the circuit only. So this fictitious battery or fictitious cell which is present in this circuit, right, is known as the induced EMF. Okay, so please note down the difference between the EMF of the circuit and the EMF of this in Michael Faraday's experiment. Alright, because this induced EMF, it comes into picture because of the current which is passing through the coil. Actually, current should be produced by the EMF only. But here there is no EMF. But we just imagine, right, when there is a current, so there should be EMF. And if the current here, it is induced current, then that EMF which is actually present, though it is, right, we cannot see that EMF, so we name that EMF as the induced EMF. And this magnitude of the induced EMF, Michael says that is equals to the rate of change of magnetic flux. Okay. And what about this negative sign? Why do we have this negative sign here? This negative sign, it is actually in accordance with one law that is known as Lenz's law. So we shall discuss this in the next topic about Lenz's law. So this negative sign, it is due to Lenz's law. Okay, so we will in the next video we shall talk about Lenz's law. And this Lenz's law, right, it tells you about this negative sign.